In this lecture, we are going to discuss about the time response analysis of control system design. So, what is time response analysis? So, before going to discuss about the time response analysis, first of all, what you have to do, we have to get the basic block diagram of any closed loop control system. So, all you know, the basic block diagram of control system is like this. So, this is your input, this is your controller block, this is your plant, and here comes another block which is known as the disturbance, and this is your output ys, and say this is your feedback block, this is hs. So this is the fundamental block of any control system. And see, this is your input and this is your output, and all the parameters are is a function of s. That means if a function of s, so all the parameters have been considered in Laplace domain, but it is a function of s. We are actually discussing the time response analysis. So in nature, basically what happens, any kind of input to any kind of system, for example, you are going to have a certain heater, that means the output of a heater. So output of a heater is temperature, this is your heater. So this is your system and this is input is heat. Once you heat this coil of the heater, then temperature gets rise, right? This is kind of system, and that means this heat and this, when you are increasing the heat, that means that is a function of time. And such that in every system, and there may be the chemical process, there may be the your hydraulic process, maybe the thermal process, whatever the different kinds of systems available in nature, the inputs are always the function of time. And similarly, when this input goes to the system, say this is your system, definitely you will get the output which will be again function of time, right? That means the system whatever available in the nature are continuous function of time. That means its input and output varies, with time. Input and output varies with time. What does it mean? Does it mean it means that its amplitude varies with time, maybe like this, maybe like this, maybe like this, whatever may be the different types of shape, but its amplitude normally varies with time, maybe input and maybe output. Okay, now whatever I'm discussing, this is your basic block diagram. And if this is your basic block diagram, see this part, for simplicity what you've done actually, for simplicity, this part is taken as the GS and WS is taken as 0, right? So WS 0, that means, and what I've told you earlier, that W is the disturbance, because whenever any process is running, so there is certain kind of input, you know, but you never know what is the disturbance may come to the system whatever during the process is running. So for our simplicity, for the calculation purpose and for understanding the system, we generally use the WS equal to 0. WS is equal to 0, that means your disturbance signal, this is known as the disturbance. And disturbance calculation to make the calculation easier. So how the overall system look like? This is your input in Laplace domain, this is your error block, and this is your GS, that is known as the forward block transfer function, as you know from the previous classes, and this is your HS, that is the feedback path transfer function HS. And also if the feedback is unity, that means for unity feedback system, we know for unity feedback system HS is considered to 1, and once HS is equal to considered to be 1, that means this is a single line, right? So this is your input, this is your output, and this is your transfer function of the system. So you know the basic definition of the transfer function. Now in order to get the performance analysis, that means for by using this time response analysis, we actually analyze the performance of the system for various kind of input, right? And the nature of the input always is not known or maybe varying during the procedure. So the performance of the system basically depends upon the you see system performance depends on the factor like the nature of the input, the disturbance, and number 3, your system characteristics. So we have neglected this disturbance part, or the system is so designed such that disturbance may be eliminated. May not be completely, but maximum elimination of the disturbance is possible in most of the cases. So the system performance in this part we will discuss depends upon the input and system characteristics. Now what about this input? Input plays very important role. You see, for any system which is running, so input may be different types. What are the different kinds of inputs? You see, there may be shock. Shock means suddenly there is a high value of input, and before there is no input, no variation of the input, and after certain time interval there is no variation of the input. So this is known as shock type of input, and mathematically this is denoted by impulse, or that is known as the impulse, because in order to get the time response or performance analysis of the system, so this is your GS. So RS plays very important role to get the output wise, and in every case this RS is varied. So according to this, YS will be varied, as you know from this transfer function. So YS equal to nothing but RS into GS. So GS, characteristic of the GS we will discuss later on. So now what kind of defined inputs may vary in case of time response analysis. Next part, sudden change in input. Sudden change in input means, say for example, at t is equal to 0, the magnitude is 0, and after t is equal to 0, at every time the magnitude becomes 1. Suddenly you change this magnitude, right? So that kind of change of input is known as the sudden change in input, and that is mathematically represented by step signal. So impulse signal, step signal. Next, the change in velocity. Change in velocity type of input. Say change in velocity type of input, you see this is your amplitude, this is your time. So this is your variation of the amplitude with time, right? This is one kind of ramp signal. Similarly, there is certain fourth type of input is there, that is known as change in acceleration. Change in acceleration means this is your amplitude, this is your time, so this is, so this type of input is known as parabolic in mathematical form. So based on the experiments or experiences, it has been observed that if these four type of inputs can be analyzed to get the system performance, then it will be sufficient to deal all kinds of variation of the inputs whatever may coming into the system input, right? For any kind of system, thermal process, hydraulic process, pneumatic process, chemical process, whatever the different kinds of process plants are available, and based upon the experience it has been shown that for the time response analysis of this control system design, the input may be of four kinds: this impulse type, step type, ramp type, and parabolic type. So here we will get first of all the mathematical form of these different types of input, and when this type of input will be applied to any kind of system, how the output is coming, that I am going to discuss in detail later on. So what we get, the different types of standard inputs signal. So there are four types of standard input signals. Standard input signals, and we will discuss about them. Say first of all impulse. How the impulse signal will look like. Say mathematical expression of the impulse. What is this? At say impulse RT. We see it RT. RT because why we are taking is RT? First of all, let me clarify it. We are taking this RS, that is your input, in Laplace. This is your GS and this is your output. Now this is actually available in time domain. We have already said that all the signals available are continuous function of time. So actually RT is your signal and you get the Laplace transform of it to get the RS. Why the Laplace transform is taken? To get the easier algebraic manipulation. So to make the solution easier, we have to take help of the Laplace transform, nothing else. So basically this is RT. That is why we are telling the function of the impulse is RT is equal to 1 for t is equal to 0 and 0 for other values. That means if you just draw the graph of it, this is your RT, magnitude of RT, this is your time 0 to infinite, minus infinity. So time ranges from minus infinity to plus infinity. See, RT is equal to 1 for t is equal to 0. That means at t is equal to 0 only, you will be having some value. This is 0 plus 0 minus, and rest of the values of t you will be having the value of RT is equal to 0. So this is your mathematical form and this is your corresponding graph, and corresponding to this Laplace transform of RT, that means RT Laplace transform, if you get the Laplace transform of RT, you get RS, that is equal to 1, or that is somewhere written as delta t, general form. So that can be also written delta t. Now this is your impulse. Next part is your step signal. Step signal, mathematical form of step signal is RT equal to 1 for t greater than is equal to 0, 0 for t less than 0. So if you just take the Laplace transform of it, you get RS is equal to 1 by S, right? And the mathematical this graphical expression for RT, you see this is your t is equal to 0, you get the t is equal to 0 and onwards in the positive direction. So starting from t is equal to 0 up to this line, you get same value 1. So this is known as unit step signal, because unit step means its magnitude is 1. It may be magnitude having 10. So in that case, the step signal with magnitude 10, that will be called up. And next part is your ramp signal. By the name you see, this is ramp. Ramp means is RT is equal to t. That is, there is a slope, because you see the graph of the ramp is like this. That means its RT magnitude changes with time like this. So there is a slope, right? So that is why this is known as ramp. as you see, this is kind of ramp, and you goes on, that means you can move over this like this. So that is a kind of ramp signal. So RT is equal to T, and if you get the Laplace of it, you get 1 by s square. And what is the mathematical form? Actually, RT is equal to T for t greater than is equal to 0, and equal to 0 for t less than 0, right? So t start from 0 to infinite, you get this signal RT, and t less than 0, that means in this direction the value of RT is equal to 0. And final form, that is your parabolic. So that is your parabolic signal, which is also used as the input signal. So that is parabolic signal. And when already we have discussed the different kinds of okay, let me finish it. Parabolic signal, so RT is equal to t square by 2 for t greater than 0 is equal to 0 for t less than 0. And mathematical form is like this. So graphical form will be like this, like a parabola. This is the part of the parabola. And Laplace transform it, you get 1 by s cube. So you see the nature of the inputs. Already I have discussed about the different kinds of inputs for any kind of process, that is shocking. If the input is like shocked, so what happens? Suddenly you get one and nothing else before and after that. So that is kind of shock, and that is a step signal. Sudden change is like this. At t is equal to 0, you see there is a sudden change from 0 to 1. Magnitude is suddenly changed at t is equal to 0 from 0 to 1 and remains same, right? And this is your velocity kind, because rt is equal to t. If you get the that means derivative of it, what you get, if you get the derivative of it, just drt dt, you get 1. That means derivative of ramp signal will give you step signal. That is usually known as the velocity change. And this is acceleration change, because when you get double derivative of it, then only you get the step signal. That means single derivative of rt with respect to t will give you the ramp signal. So these are the relationship between these all types of inputs. So derivative of parabolic signal will give you ramp signal. That means in a simpler way I can write like derivative of ramp equal to step, ddt of step will give you impulse, and ddt of ramp will give you step. So these are the relationship between these four types of input. And similarly, once you get the derivative of step is equal to impulse, that means integration of the impulse will give you step, and integration of step will give you ramp, and integration of uh, uh, sorry, this is double written actually. So this will be ddt of parabolic equal to your ramp. So integration of the ramp will give you the parabolic signal. So these are the mathematical form, graphical form, and the Laplace transform of the different kinds of standard input signals, and which are very much essential to study our time response analysis for any kind of signal, any kind of system. So the input signal are described. Now the different types of system, now I am going to discuss system. So system is normally denoted by GS, and you see the properties of the system already in the first lectures. On the previous lectures we have discussed the order and type. The system is identified by its order and type. So what does it mean by order? Say for example, we get the transfer function of any series RLC circuits. So series RLC circuit, we get, say this is R, L and C. So this is your applied voltage V1, and you get the V2 across the capacitor. So GS, what will be the GS? as we already discussed the mathematical modeling of the systems, that means what is actually acting behind the transform function. Whatever we are telling that this is a second order system, say for example gs is written like 4 by s squared plus 8s plus 16. This is a type of the, that is one kind of system is given. So what does it mean? That means this 8, 16, 4, these are the coefficients actually coming from the values of r and c. So whatever you are talking about the type, whatever whenever you are talking about the order, that means actually in the background different types of maybe mechanical system, maybe electrical system, maybe a pneumatic system are running. So coming to the point, so this is your, say for example one transfer function. From this what you see there is a there are two poles, right? And this is known as the, when this is closed loop system. So if this is your closed loop system, we already have discussed about the closed loop system and open loop system. So closed loop system, this denominator is known as characteristic equation. What is this? This is your characteristic equation, because from this equation, that means from the solution of the, from this equation means actually solution of denominator will give you the roots position. Roots position means what? Say for example take this transfer function. So denominator is s square plus 8s plus 16 equal to 0. If you make this denominator is equal to 0, so characteristic equation, this is known as the characteristic equation. So characteristic equation is nothing but the denominator of the closed loop system. So denominator of the closed loop system is the characteristic equation, and if you make this is equal to 0, then you will get two poles, right? You know the concept of poles and zeros. That means when you solve the denominator and get the value of s, these are known as poles, and when you solve the 0 and get the pole position of the s, that is known as zeros, right? So this is the concept of poles and zeros. Now if you solve this, what you get? The two values of s, two values of s, right? What are the different values you can get by solving this using the Sridhar formula? So you will get say s1 and s2. These are the two values, and these are known as the roots, and position of these two is very important for us to get the performance characteristic of any system. Position means what? Positions mean we have to describe this in detail using the Laplace plane. Like this is your Laplace plane. So details about the position, that means how the poles are located on the S plane. This is known as S plane, which is having one real part, one imaginary part. So this is the complete S plane which varies from minus infinity to plus infinity. So within this plane, anywhere this S1 and S2 could be located, and by seeing the locations and shifting the locations, the performance of the system can be analyzed.